Okay. So welcome to another Computer Musing, and I hope that you people enjoy seeing work in progress as much as I'm having fun doing this work. What I want to show you today is done with the help of two wonderful students. Well, I might as well introduce them right away, Robert Bosch and Chris Stolte. Robert and Chris, stand up for goodness sake. Anyway, Robert's going to have to come here and fix it. These are, when I say work in progress, I mean that these guys haven't had any sleep for the last 3 days, and we built the system that you're seeing demoed now about a half an hour ago, and we've been making great improvements to it all the last several days, and it's fantastic to work with these guys. I never known two people before who could sit in the same office and both work simultaneously on the same program and perfectly reinforce each other and get stuff done fast. We get an idea and then it's implemented a few minutes later. So 3 weeks ago I talked to you about MMIX, this nice clean risk machine that I've been playing with and intending to use in the next edition of my books. And today I want to show you the simulators that we're building to test out the ideas and check them. Last Thursday and Friday, last Friday and Saturday, I designed and sketched out the program for the assembler for MMIX, and on Sunday I did the programs that would simulate the multiplication and division. And then Monday, Tuesday, and today we've been working on this part of the simulator. I started working on the pipeline simulator actually, though a long time ago in November, and it's I would have to say it's one of the most interesting programs I've ever had the pleasure of working on. And I want to explain about pipelines today. But this is a program that has very interesting complexities. The way computers parts of a computer interact with each other, and I want to show you some of the reasons why I think they're neat. The program itself isn't finished, but I can show you the main part of it. Can we maybe get this on the screen? Does your camera pick this up, or do I have to move it over? Here you can zoom. So this is the table of contents for the main part of the program, this is I like to write in C-Web. Can you see that a little bit? So introduction, low-level routines, coroutines, list, dynamic speculation, dispatching, execution, commission, deissue, branch prediction, cache memory, simulated memory, cache transfers, virtual address translation, the write buffer, loading and storing, fetch stage, interrupts, administrative operations. You could probably bring down the house lights. More register-to-register ops, stuff for later. That's what I haven't written yet, and so on. Now this program has enough complexity to it that I personally think that there was no way that I could have ever written this without a tool like C-Web. This idea of literate programming has now, in some ways, a program this complex. I doubt if I could ever have gotten anything like it with this complexity working in an understandable fashion if I hadn't used this way. Now, I say a little bit about literate programming because in literate programming you try to write for human beings to read the program and not just for the computer to understand the program. And I'm hoping that some of you in the audience will enjoy reading this someday, because I plan to put this into a book. There will be a book called MMIX and let me read you first something about pipelines from the introduction. It says, one way to visualize the procedure of pipelines is to imagine that somebody has organized a high-tech car repair shop according to similar principles, similar to a computer. There are 8 independent functional units in this car repair shop. We can think of them as 8 groups of auto mechanics, each specializing in a particular task. Each group has its own workspace with room to deal with one car at a time. Group F, the fetch group, is in charge of rounding up customers and getting them to enter the assembly line garage in orderly fashion. Group D, the decode and dispatch group, does the initial vehicle inspection, writes up an order that explains what kind of servicing is required. The vehicles go next to one of 4 execution groups. Group X handles routine maintenance. Groups XF, XM, and XD are specialists in more complex tasks that tend to take longer. The XF people are good at floating the points, while the XM and XD groups are experts in multi-link suspensions and differentials. When the relevant X group has finished its work, cars drive to M station where they send or receive messages and possibly pay money to members of the memory group. Finally, all necessary parts are installed by members of Group W, the right group, and the car leaves the shop. Everything is tightly organized, so in most cases the cars move in synchronized fashion from station to station at regular 100 nanocentury intervals. Now this is very much the way a computer pipeline works, and let me show you a little bit of this demo first by starting in the middle of it. It's a program that I'll explain to you a little more as time goes on, but let me first just go to a sort of a steady state part of it. Whoops, I got to hit the control thing here. So let me just go up here. It's a program that calculates half of a decimal integer. It starts with 1 and then it gets 1/2, 1/4, 1/8, 1/16, and works in decimal. And as it's writing the answer here, you see it in the right buffer a little on the left there. It's written in ASCII code. So 30 is a 0, 30, 30, 30, 37, 38, 31, 32, 35 would be 0.0078125, which is some negative power 2, I think, or at least maybe somewhere in the middle of a step. You can sort of see these. There's some pulses in here that you can see. The vertical lines mean that we've actually written a character to the right buffer, and then when there's a little gap between, that means we've actually finished power of 2. Here we've computed half of the previous one, and then another half, and another half, another half, and so now we're in the middle of taking half of the thing that we got on that cycle. So now you can see that there are 2 instructions in the pipeline right now. One is that light blue one at the top in ALU1. It's up here. And then there's another instruction, the green one here, in the load store unit, LSU1. Over here is the F group, the fetch buffer. This is where instructions first come before they're executed. It happens to be empty at the moment. I'm not sure why, but it might be a bug, but I don't know. I think it's probably okay. Yeah, it's because this instruction in the ALU here says probable branch if a non-zero. And so since it was a branch, a probable branch, then we cleared the fetch buffer, assuming that the branch would be taken, and we're trying to get the we have to get instructions from another place. So we're branching. That's why the fetch buffer is empty at this point. We're loading a byte. This is an LDB instruction. So we're loading a byte into some register, and so these are the execution units. In this particular version, we have 2 ALU, 2 arithmetic logical units, and 3 load store units. This particular program isn't using them. I believe it would run exactly as fast if we had only 1 ALU and 1 LSU. But the simulator, that one of the things that makes the simulator interesting is that it is infinitely configurable. I can say I have any number of units of any kind. I can take any subset of MMIX's operation codes and say I have a functional unit that can implement this, and I can have as many of these as I want. For example, and there's many other ways to describe the simulator. Each of these ways would be a conceivable way, perhaps, to build a real MMIX machine. So instructions are first fetched, and then they're dispatched into one of the execution units, Then after they're done executing, then they go here, and this is called the reorder buffer. And the technique that we're using in this pipeline simulator is called dynamic scheduling with speculative execution. I'll talk more about what that means, but essentially it says that the computer decides as things come out of the fetch buffer which execution unit should take them, and then and it'll also start executing instructions ahead of time before you know they're really needed. And then some instructions take longer than others. For example, a division takes 60 cycles. It's the longest instruction in MMIX. Multiplication takes 10 cycles, and add takes 1 cycle. And so sometimes instructions have to wait because they depend on each other. And here in the reorder buffer, we have one instruction here. It says inkle. This is increase the lower wide of a register, and it's ready to it's finished. But the other two are grayed out, which means that they're waiting. One of them's waiting for this one, and one's waiting for this. And the instructions will leave the reorder buffer in the same order in which they entered. And so I'll let me just run one step to show you what will happen on the next cycle. Okay? Do you see that? You want to see it backward? Go back again. So this is where we were. Now that was cycle 679. No, that was okay. Let's go forward 2 now. So here's the probable branch going in there, and then the two things are going into the reorder buffer. Maybe I should stop it. So you see the instructions play a little dance as they're going through the machine. Now we've got two things in the fetch buffer: a load. This is a load byte and an incl, and then the load store unit here has a store byte instruction, which is going to store a byte in the write buffer. And this is a two-stage process. At first, on one cycle, it has to figure out which byte, the virtual address that it's going to store into, and on the next cycle, it'll actually do the storing. These things will complete and go into the output on the next cycle. This is waiting for the store to finish. From the fetch buffer, we should be able to get the incl instruction into an ALU at this point, and I think the store byte is going to go into the second stage. No, it didn't go. Yeah. The store byte went into the second stage, but the load byte went into the second load store unit in this case. Now, if I had only one load store unit, it would have gone into the first one. But since there are two, it's safer to go into the second because you never know. The first one might stall in the second stage because it can't find the data in the cache. The cache might be busy or something. So that's now. It was serendipity that I happened to run into Mendel on the steps a couple of months ago, and he said he had two students who were doing research on how to visualize pipelines, and that's how come I met Robert and Chris, and they had been making such visualizations for real computers like the MIPS 10K machine and so on. And it's amazing when you have a tool like this for visualization how much easier it is to understand what's going on, to find bottlenecks, and to see what things work and what things don't work. So this is but now ideally we would like to issue one instruction with this particular machine. It is set up so that it issues one instruction on every cycle at most, and out of the reorder buffer, it commits one instruction per cycle at most. We can also configure the simulator so that it's superscalar, which means that it will allow several instructions to be to be committed at a time and go into execution, and several instructions to be several to be issued at a time, several to be committed. I talk a little bit about terminology here. I find out that when the students were talking about what happens to instructions when they leave the reorder buffer, they said they graduated. And although in John's book he calls it committed. Well, yeah, I guess I can see why graduation is important to a student. But the other thing I learned was that the students their natural inclination was to put things in the other order. They had things at the bottom of the reorder buffer and sort of falling out at the bottom. And similarly in the fetch buffer, they were coming in from the top and dropping down and sort of sinking down. And I don't know. That's not my model of students. It seems to me that students are rising, until they finally, when they graduate, they aren't settling out. They're actually, going up to the next level of challenges. Well, but anyway, maybe this is just a difference of generation gap or difference between the way people think on the third floor and fourth floor. But I insisted that they put these instructions.
But faculty think of graduation as the beginning.
Yes.
Of
yeah. So this is going on. Yeah. Okay. Anyway, but these instructions now appear as they would in a program. So as you write this as you write this program, you have an increase L load byte probable branch, and they appear in that same order here. And similarly in the reorder buffer, they appear in the way they would appear in your coding form. So that it had to be that way for me. Now this little strip chart on the bottom shows every cycle of this demo in a condensed form, and so it'll show you the reorder buffer, but the things are sorted by color. So things that belong to the ALU are this light blue color, and a darker green color are the things from the store buffer. And there's interesting things going on here. You see these waterfalls and mountains at the left. And I'll talk about that later. But we have exactly 2,000 clock cycles shown here. We figured it was probably dangerous to go beyond 2,000. Everybody knows that's a hard number to pass, so we stopped there. This program I'll show you actually does go on and on. It keeps on. In fact, it never stops, but I could run it a lot of time. Now, okay, any questions about this? No questions. Maybe I didn't explain it well enough. Okay, so now let me show you what let me show you the program that is executing and something about it. So let me see. That's F2, I think. What it takes away, and now I get to Emacs here. Okay, so now I hope I'm in the right. Let's see. I'll show you that program that we're taking halves. MMS file. So this is a program that I won't dwell on, but this is a draft of the assembly language for MMIX, and the program that we're actually running here. Let's see, how do I get this to scroll up on this machine? I don't know. So it's a very short program that that has this little loop here. It jumps into the middle of the loop, and then the loop is 7 instructions long, and ending with this probable branch, and then goes back to the loop again, and then after you get to the end, this is all working in decimal arithmetic as a string, and you can see it's sort of a C-like syntax at the right in the comments. But it's it's a 7 instruction loop, and it's designed so that each instruction, except the branch to the beginning of the loop, should go in one cycle. And then at the end you finish and you go back and start over again and then take half of the number again. But we also had a okay. So then I hand assembled it, because I said my assembler, I'm just writing it. So I hand assembled it into binary, into hexadecimal, and so the instructions are here in these places with the comments at the right, and Remember, MMIX instructions are very simple because they have 4 bytes. The first byte is the operation code, like C1 is the operation code, and F8 would be P, FA would be P base, and so C1 would be the OR and immediate instruction, and so on. So it wasn't hard to hand assemble this stuff. And then we put in the data, and there's a table here that has a table of what's half of each byte. And so then in order to get the program started, we have to load the context, and so the very beginning of the program, I'll show you, is the way the loading routine gets things off the ground by doing MMIX's unsave instruction, which means take a context, all the registers, and go into and put them all out of memory and into the real registers, and then we're ready to begin the program. Then there's a configuration file, and let me show you that. So that would be halves dot. Now let's. I think I used it. Okay, I used primes dot mconfig. I use the same configuration for this program as I did for a primes test program. I'll show you later. But this is typical of the kind of things that you can configure in the simulator. So here we say mem address time, mem read time, mem write time. This is how many cycles does it take to send an address to a physical address in memory buffer, in memory bus, and how many cycles does it take if you want to read? How many cycles before you get the data on the bus? How wide is the memory bus? Here, in this particular case, we're taking 16 bytes at a time. Here I've commented these lines out because I found a bad bug in my branch prediction mechanism on Monday. And I didn't have time to fix it before today, but I have. But one of the things that you want to do on a machine like this is to do the best possible job of predicting when a branch is going to be taken, and I have a general mechanism that I know I can fix, but it doesn't work at the moment, so I commented these out. But it allows you to base a decision on the next branch based on a combination of where you are, where's the instruction that's branching, and what's then the past history of branches before the current one. Then you can also say how there's also a number of bits that you in your prediction table. Here I've used the default of 2. Okay, so then mem chunks is not important here. Now it's important to gain speed because the memory is so slow. It's important to gain speed by putting the recently used parts of memory into caches, and there are in this particular case 3 caches. All the caches are optional except the caches for translation from virtual addresses. But here I'm using optional cache, so I have a secondary cache which has 64 bytes in each cache block. And 512 sets with 4 in each set. This is 4-way associative cache, and it takes 2 cycles to find out whether something's in the cache or not, and to get it if it is. The D cache has a smaller block size and it has smaller sets, and this is for data, and the I cache is for instructions, and also has a so-called victim buffer, which means that if you throw something out of the cache, in this case I'm keeping 2 of them just in case that they're going to be needed. This is not these have no associativity given, so that means that they're directly mapped caches with only one thing in every set. All of these things for all of the caches can be specified, and also including the so-called victim replacement policy. There's I can tell you what pseudo-LRU means. for those of you who know this sort of thing. Can you get my pad on the screen? The pseudo-LRU for four-way associative cache is something that was used in some Intel machine, and it generalizes to any power of 2. So let me show you what it would be like for an 8-way associative cache. Although I don't know if anybody's ever built one of these. It's a little bit expensive in hardware to keep track of exactly which was the most recently used block and the second most recently used block and so on. So instead, but let's imagine there are 8 blocks. But what you sort of want is that if you've used a block, you don't want to take it out of the cache. You want to say this is a good block to keep. So the pseudo-LRU scheme, a true LRU scheme would say every time you use a block, you put it at the end of the line, and you take it out of where it is and put it at the end of the line, and you keep on doing this, and you have to remove a block you take from the front of the line. The pseudo-LRU is simpler. It needs only it arranges these 8 blocks into a tree and has routing information where you have a pattern of bits, zeros or ones on each node of the tree. Let me just give it a random example here, telling you whether you want to go to the left or to the right when you're in order to find the one that you're going to remove. So this case would say 0 says go to the left, 1 says go to the right, go to the right. So the next one to be removed would be this one, following this routing information. 0 is left, 1 is right. But now when you use a block, you set all the bits to go the other way. So suppose I now use this block. So that says, okay, so then I'm going to change this bit to a 1. So that'll always go, I'm going to change this bit to a 0, and I'm going to change this bit to a 1. So that this block it'll be hard to evict this block next until all 3 of these bits have changed. So this is the idea of pseudo-LRU. It's and with the simulator we can find out whether whether that behaves any better than random choice or any better than a true LRU and so on. So there's lots of different parameters that are settable. Here I've defined the units, and each unit is defined by 256 bits, saying which opcodes it will support. And so in this particular case, this one doesn't do any of the floating points, and then it starts doing add and subtract and so on, and then it doesn't do the load stores, which are here. And here's a load store unit which does the load stores, and another one. Here's a multiplier unit which picks up the multiply instructions, both floating point and fixed point in this case, and here's a divider unit. Floating point unit picks up the other floating point. This is just, but any combination of things could be used. You could have one unit that's just good at shifting and taking AND and OR or whatever. Here you can say how many instructions can be dispatched on every cycle, committed on every cycle, fetched on every cycle. You can say how big the fetch buffer is and so on. How inside of the reorder buffer, there's a certain number of temporary values that are called rename registers and slots for storing, and so that depending on how much capacity you want, you can set these things. You describe for each cache whether or not it's right around or right allocated. When you have a miss, do you want to evict something else from the cache, or do you want to or you just want to send the thing on to the next level of the hierarchy? Right back or right through is another possibility. So all of these, you can see that that sort of a non-ending list of possible things that a hardware implementer can choose between, and it's very difficult to understand the trade-offs between these things. Not to mention the cost that some of these things involve. With a simulator like this, you can try all kind of combinations, even ones that you don't know how to build. A lot of these things that I simulate, I really have no idea if it's even possible to do in hardware. Least recently used caches that are 16-way set associative with 4 simultaneous read ports or something like this. But you can find out if they if they really save you, and you can run it on programs and see if it actually makes a tremendous performance increase or not. And if it does, well, you'll probably figure out a way to build it. Otherwise, you'll know that you'll say, oh, good, I don't have to figure out how to do it. So this says that there's 4 things in the write buffer, and this says that we keep things 5 cycles in the write buffer, hoping that that something else will want to go in the same location before we actually decide to go to memory. So this is an example of parameters. I'll show you another file quickly. This primes x.mmconfig. This one is similar, but we added a couple of ALUs. Has 4 ALUs, and the main thing I want to show you at the bottom here, we defined undo this. We defined that the division is going to take 6 stages in 6 pipeline stages, 10 cycles each, instead of 60 steps all in one place. So that means that that there are 6 places where people can be working on parts of the divide. See if this speeds programs up to have a divider with 6, which is pipelined in this way. I could have made it 61s, or I could have made it 1 followed by a 59 or anything. But all of the instructions that are potentially time consuming, a floating point, multiply, even shifts, you can specify the running time and to what extent things are pipelined. So this is a configuration file. Now when I run my simulator, which is called MMIX, I have a config file first and a program file afterwards. So I say MMIX, for example, halves dot mmconfig. Well, actually, I used primes, didn't I? So I'll go back. Primes mmconfig, and then the program file was halves dot mmix. And so now, to get started, I have something called D, which is for debugging. This is just to get going until I get my assembler and loading routine working. Then I have another thing called K for kludge, which is just for this lecture. But D and K are my initials. So and this prints out the units and the number of stages in the units as a hint to Robert and Chris. Now I can say do 1,000 cycles or something like that. But let me just show you the pipeline. P says show what's in the pipeline. So at the beginning, that's my kludge, was it the kludge or the D? I think it was the D that did this. It put into the fetch buffer something that would we bootstrap the program. The important thing is this unsave instruction here, which says the first 2 instructions put something into register 0, and the second one says unsave starting at the address in register 0. And then we go to the contents of register F4, which is the way the program is going to start. So at the beginning, we have to bootstrap, so you have to get going and fill all the registers with stuff from memory, and then go. It says instruction pointer is waiting for dispatching. And so if I said verbose to print everything out and do 1 cycle, we can see that what happened at cycle 0. It runs the write. It runs a program that looks and sees if there's anything in the write buffer, which it doesn't find anything, and then it sees if we're ready to fetch anything. It isn't because the instruction pointer isn't there. So then we scheduled something for ALU1, an instruction that increases register L to 1 because you can't put anything in register 0 unless we have 1 local register. This is a technicality, but anyway, this happened. And so we issued the first instruction, and we left instructions in the fetch buffer. The next cycle does, I'm not going to take you through this whole program, but I just wanted to show you something of how the simulator works. So it has to check some things. It issued this set instruction, which is setting the value of register 0, and then in the reorder buffer now we have 2 instructions. Now this is the information that I gave to Robert and Chris. a trace of this for 2,000 steps, showing what the simulator did. You know, in the future, of course, it's simpler if we just plug in there, because there's hooks in my simulator, and their visualization routines could go directly from the simulator. But at the moment, it was certainly much more convenient, since we're changing everything all the time, is to work from stored log files of what happens. If I set verbose to 0, it's not going to print them. I can now say go 2,000 steps, and it goes 2,000 steps. You know, it doesn't take any time. And I can look at, for example, the dcache, and the dcache will show me the values that I said D star, which meant show me only the values that are that haven't been stored in lower levels of the hierarchy. These are the things that have actually been written out. So in this particular case, I've written out the numbers 0, 0, 0, 0, 0, 0, 1, 9, 3, 0, 7, and so on. And if I wanted to see the entire dcache, it would have had you know, other things in it that had been loaded in. Okay, any questions on this? You get the idea? Yeah.
What's the difference between fetch buffer and inspection cache?
Okay, the fetch buffer is things that have been that are ready to be dispatched, and so it goes from the current instructions. Let's take a look at fetch buffer here. So actually, the zeros here are fake. This is usually the address that's in. So let me give you a better example. I'll turn on verbose mode again, and wait, what happened? VFF. Okay, I had something in Emacs. And now let me run another 1,000 cycles. What the heck? This will we'll be able to go and see the fetch buffer. Let's see. Let's go to cycle 1,200, 2,000. Let's see. I'm sorry. This is a slightly brain damaged Emacs. So like, what did I say? 2,100. Okay. So here, now we can start looking at fetch buffer. So the fetch buffer here has two instructions in it from 1020 and 1024. Okay, each instruction 4 bytes long, and these are instructions that are waiting to be issued. So at the next time we would issue this load byte instruction, and this if you know unless there's no unit ready to take it, and so here it is in fact issued at this point. Okay, and then it leaves the fetch buffer, and now has only the probable branch instruction in it. Instruction pointer now is 100C. You see this? That means that the probable branch was an instruction that this simulator peeks ahead at the fetch buffer. Even though it issues only one instruction on a cycle, it also looks at the next one to see if it's going to change control. Gives it a head start, so that if the branch did occur, we don't actually lose it. We don't actually lose from it. So at this point, though, the fetch buffer it didn't fetch from 1028 because it knows that it should go next into the other place. Okay, does that answer your question? Now let's take a look at that trace and again and see what happens. So oops, where was I? Have this one maybe, and this one. So now if we went back to the beginning of this program, you'll see how it started up then. So at cycle 0, it has these 4 instructions in the fetch buffer: set, increase, unsave, and go. So now I'll change it to fast, and we'll see. So it'll start the first cycle. So now the unsave sits there for a while. The unsave generates a whole bunch of instructions into the load store unit because we have to unsave the context. In fact, it's at least 14 octobytes of information to get going, and up to more than almost 300 if you save the large context. It takes a while. It looks like it's stalled now, but in fact, what's happening is, if you look down here, you see the main memory is lighted up. That means that the memory is locked, and the memory is actually feeding, and the S cache is lighted up too. That's why, and you see it in the script here too. That you see these things at the bottom of the script. That means that the memory, the bottom line is this red line for memory, and then the S cache is yellow. The D cache will be blue when you see it in the I cache green. The main memory is busy now. Oh, it finished, but the S cache stopped filling. Now the D cache is going to fill. Okay, so now we got to get the information into the data cache in order to load it in to a register. And then that was good, but that was only 32 bytes, and so we have to do it again. The S cache actually got 64 bytes, and so the D cache will come up fast. Anyway, it takes a while, and that's what all of this stuff at the beginning is, getting all of that stuff out of memory, and so we have to sit here, 10 cycles just to read 16 bytes out of memory. So that's what happens at this point, and then the unsaves have filled up the reorder buffer with 6 load instructions, and they're sitting here in the load store unit. In the first stage, in the second stage, they're pounding on the D cache, saying, "Is this? Please give me this data." In the first stage, they're saying, give me a second stage to go into. I'm stalling here because now this can go in the second stage and say, give me this address, and so things will gradually come out of the reorder buffer. Okay, I can move faster here past this until we get to the next stage, and when the program is about to start. So let's go ahead here. Okay, so unsave is still happening all this time, and it gets a little boring after a while. But in fact, this is what happens in machines. You have to realize that we don't think about this when we're writing a program that it takes a long time to get going at the beginning. Fortunately, that's only once, and still 225 cycles. I mean, if we're running at 225 megahertz, this has only been 1 second. So. Microsecond. Yeah, 1 microsecond. Factor 10 to 6. Yeah. So, okay. So unsave. Come on. Go. Now, unsave is done, and we're doing the go instruction. Now it has to go and fill the I cache. So watch the I cache light up here. We're ready to start. Okay. So now the I cache is being filled, and the memory is now reading into the S cache from a different place. Now it's reading from the place where the instructions were. Before it was reading from the place where the data was. Okay, and so then it goes through this long dormant phase here, you see, in order to get the instructions. So then we get finally into the program itself, and when the program is going, it still has, the memory is still busy. We haven't actually been able to write anything yet, and so things are building up in the reorder buffer. So these are instructions that have, the ones that are bright lighted here have completed their operation. They're no longer in a functional unit. The functional unit here is this store byte instruction is what it's probably waiting for. It's waiting for a place, because you can't store a byte without reading what the other bytes were in the word that you want to store into. So it's taking a while to before it can do the store byte. We should get something up into the D cache in a minute. Yep, there it comes from the D cache. So pretty soon we should be able to hit to see something in the write buffer. I'll advance this 20 cycles. Now you see in the write buffer this 0 here. Well, it started with 1, and it should make this. Are we still going? No. Okay. So it should store a 5 here, and then we should in a minute. But main memory is still locked, so we're still bringing stuff up. As soon as Yeah. As soon as I get to this store byte here, that's going to store the 0.5, and then it'll begin. But notice we got the reorder buffer really full of stuff here. This is now, and because this guy, it's waiting for this guy. As soon as this guy is done, then he's going to commit or be graduated. So things are going to start happening. See, watch him move out of the reorder buffer and go down. Okay. Questions on this?
What do the colors on the reorder buffer mean? Why are some
I
instructions?
can't hear you.
What do the colors in the reorder buffer mean?
Okay, if it's brightly lighted, that means that it's already out of the functional unit. Otherwise, it's the color from the functional unit. So the green would come from a load store and a light green from an ALU in this particular case. And we're going to have another color for divide in the primes example. And gray means it's sitting in here. It'll be a grayish green or a light grayish green or something like that. So here you see then with a solid dark green at this point because it was all load store, and it was a light green here because it's all ALU pretty much. And here was a mixture of the two. We had a whole bunch of load store mixed up while we were waiting for the cache. Okay, see this is lighted up here 1, 2, 0, 1, 2, the 5. 0.0125. So that's in the right buffer. We've just computed 1/8. Okay?
In this particular case, you're just displaying the trace information. Is that
We're
correct?
displaying the trace information at this point. I'm not actually running the simulator.
Okay, you're not actually running the simulator.
Their simulator goes off of the log file. In fact, they parse the log file. And we won't have time. We won't have time today. But it would be nice if if we had extra time for if I could go through the audience and say what parameters do you want, how many registers do you want, and how big a reorder buffer, how much fetch buffer, and everything, and then we could we could do it, and it would only take 3 or 4 minutes to set it all up and make it work. But I have other demos that are pre canned, which I think will give us the same kind of information. But you can play with this endlessly. It's a wonderful toy. In fact, we would often write programs and we had no idea which way it was going to come out, and then we would see what we thought was the bottleneck. And so I said, oh yeah, the program is starved. It needs a bigger fetch buffer. I increased the size of the fetch buffer, did nothing, because it turned out that the bottleneck was really because the fetch buffer had to be cleared because of the branch instructions. But now I'd like to show you a version. Yeah, go ahead.
Is it possible to describe a situation where several execution units capable to execute the same instruction, but say with different timing for different number of cycles?
Yes. I'm not sure I quite understand. So, you have several units working on the same instruction?
If you have the different type of, say, float point units,
yes.
One is capable to execute division for 50 cycles and another one for, say, twice longer. Takes twice longer.
Oh, okay. Yeah. Right now I haven't specialized it. I haven't specialized it that way. I have only one table entry in my config file for floating point multiplication, for example. That would be not hard to add, but at the moment it's not that general. And I don't even when I say that a shift left is going to take the same time as a shift right. Okay, I've got another example where I remember I showed you this configuration file where we had extra ALUs and also divide with 6 units. And then I also increased the fetch buffer size to 10, and I wrote this HASS program for that. So let me show you that. Let's see, HASS XX is this guy here. Is that right? Do I just double click on it? Yeah, it worked. Okay. Now this program, go back to Emacs. What I did for this program is I repeated the loop I doubled the loop. Remember, the loop used to be 7 instructions long, 1, 2, 3, 4, 5, 6, 7, ending with a probable branch, non-zero. So now I changed it to a branch 0 instead of probable branch non-zero, and I repeated the same 7 instructions again. That's just called unrolling a loop once. I didn't do anything fancy about interleaving the loops. I just copied the loop again. That's the only change I made to the program. But we're running now with the config file that has some lines uncommented out. See, I added 2 ALUs, but the main thing is right here. Dispatch max 3, commit max 3 means that that this is superscalar now. We can do 3 instructions at a time on a clock cycle. And I gave a fetch buffer size of 10. So now let's take a look at what happened. What was that? That was this guy here. So you see the fetch buffer here is 10, and I now have 4 ALUs, and it's going to start out with the same boring stuff at the beginning, and having, the memory is going to take the same amount of time to load that stuff up, and we're going to sit there and wait, and then for 1 or 2 cycles we'll go zing and be able to do the things out, but then we'll still be waiting for the memory again. So it doesn't really help to have the superscalar until we get going into the program itself. So let's go to to part into the middle of the program here, where it's, and start executing now with this superscalar version. Fetch buffer seems to be empty. Okay, so so here you see you want me to go a little slower? You can watch. I can go even slower. Yeah, but you see, first look at the reorder buffer. About half the time you'll see three things leaving the reorder buffer at every time. That's the payoff. If 3 things can be committed, or if 3 things can be issued, or if, and are committed, then we're using the superscalar feature of the thing. So it's going here, and going into the ALUs, and you see the gray slots. This one's waiting for something to finish. It came out of the load store. It's kind of a neat dance. Here, these 2 come in, zip, they go out. Okay, this from a small program we can see how much speed is advantage we're getting. We're not getting a factor of 3, but it is working, and I'll let you watch it a little bit more. Notice the fetch buffer is empty right at this point. That's because we did get to the end of the 14 instructions, and then we had to start over. Then I had to fill fetching again. And since we're dispatching 3 things at a time, we probably should have more than duplicated the loop. But if I had repeated the loop a few more times, then this pausing for the fetch buffer would almost never have been necessary, I think. But I haven't tried it. I have to hand assemble this darn thing every time. I mean, so I duplicated the loop only twice since I'm typing in hexadecimal stuff. Next week I'll have an assembler that make this real fast to test. Okay, so that's medium speed of that routine. Question? Let me show you the comparison of the 2. Which is it this? Yeah. So here are the time. Oh, this one's still running. That's interesting. Stop it. Fine. Well, it doesn't stop. Yeah, I see. It just took a little while for it to get. Okay, so you can see the 2. You can see how much we're gaining on it. without the superscalar, we're getting 1, 1, 1, 1, 1. Each one takes one more cycle because the number gets one more digit long every time you take half of it. And here you see it's going much faster. Okay. Now the other demo I wanted to show you is for prime numbers. You want to give me that, Robert? So the first example of a decent-sized program that I have in Art of Computer Programming is a program to calculate the first 500 prime numbers. And this is so naturally I'll probably retain that same example with MMIX as I had used for MIX, and so I rewrote it, in the assembler, and now we're going to show you three versions. One of them is where you issue one instruction at a time, and you wait, and the divide is not pipelined, and so it waits 60 cycles for every division. Now you know how to calculate prime numbers. There's many ways to do it, but this is the most obvious way. We start out, we say that 2 is prime, and in fact we even say that 3 is prime, and then we have to test. Then we're going to go through odd numbers. We're going to try 5, 7, 9, 11, 13, and so on. So is 5 prime? Well, we tried dividing it by the prime numbers, the odd prime numbers we already know. So we divide 5 by 3. The remainder is not 0. So 5 is not a multiple of 3. Looks good. In fact, that's all we have. So 5 must be prime. 7 divided by 3. The remainder is not 0. We don't even have to divide 7 by 5 because we find out that 7 divided by 3 is already less than 3. And that means that the divisor was bigger than the square root of the number we're trying. And anything that's not prime is going to have something that's less than the square root of it that divides it. So we only have to divide until the quotient is less than the remainder or greater than the remainder, one of those two. As soon as we divide by a number so that the quotient is smaller than the divisor, then we've tested enough to see that it's prime. So that's the idea of this algorithm. It's simply if we're trying to decide if 25 is prime, we divide by 3 and then by 5. See, whoops, the remainder was 0. MMIX has one thing I wish all computers had, and that is the divide and remainder are obtained at the same time. On other computers, you do a division. Almost all algorithms I know that where you want to know the quotient, you also want to know the remainder in the next line of your program. So it seems silly when you have such an instruction. You already had the remainder to have to calculate it again. But that's the way most machines seem to work. In fact, a lot of machines don't even do division in hardware anymore. But that's another story. With MMIX, we have the quotient and the remainder. One of them appears in a special register off to the side. This is the prime program. Thank you, Robert. You see, it starts out with the same bootstrapping idea, and then but when it gets going, it's a little different now than before. Because you see, it's building up a whole bunch of stuff in the reorder buffer. Let's go there and see. That looks like it's a little bit interesting enough to get into this program. So first we had a dead time waiting for the iCache to get some instructions in here. Let's look in here. We're starting to think about prime numbers. Okay, the memory is filling the S cache during this time, but we can start seeing what's happened. Now it's a little different than before because there is going to be a divide instruction coming. At the moment I'm waiting for a load, however. I'm trying to load something that's the next instruction is going to be increase add load wide. So this will be a trial divisor that we were trying to load before, so we could do a division instruction. Division instruction should come along pretty soon. let me go on. So we're building up instructions in the reorder buffer that have already been processed, but they're hanging on this load or store instruction up here.
Question?
Yeah,
You said, I thought, that you're not actually running the simulator now?
that's right. It's going from a trace.
Oh, okay.
And trace is stored, so I can jump ahead to 352 without too much problem. Now here you see in the right buffer, 2 is prime, 3 is prime. Even in hexadecimal, it's true. Okay, and let's go on. And the division is lit up here. So 60 cycles later, this division will be, this purple guy will be done. Now, in the reorder buffer, by the way, in my program, I found it was important to, writing a literate program, you want to be able to describe the algorithm in interesting terms, and I had to check also that the architecture of MMIX was going to work properly in cases of interrupts and so on. And I needed a name for things that were at the beginning, that are ready to graduate, ready to commit, and things that were fairly new. And I decided that I would say that this was the hot seat up here. The top of the reorder buffer is called the hot seat, and at the bottom, this is the cool end. So everything is cool when it starts, and it gets warmer and warmer the longer it sits in the reorder buffer. And the air conditioning is a little tricky in these chips. And so the students also made this. That's why it transitioned from blue to red here it shows in the reorder buffer. But the guy in the hot seat is this divide instruction, and it's going to wait for the divide to finish. Even if I had an interrupt at this point, it would wait for the divide to finish. But I did take account that a floating point remainder instruction sitting in the hot seat would be interruptible, because that floating point remainder might take several 1,000 cycles in the worst case. Okay, things are happening now. Even though this division is going on, nothing depends on the result of the division for a while, and so we are able to get this. Now, you see these vertical lines here? That's when something goes in the right buffer. So that shows the time when we found a prime. So we're going to find 5 is prime here, probably, or 7 is prime here, and then this will be 11, this will be 13, this will be 17, 23, 29, I don't know, 31, I don't know. We'll be able to see that. But anyway, this is the idea of what happens when you've got an algorithm that unfortunately has to wait for the result of this divide. I have to see if the remainder is 0 before I know before I can go on next. Even though I've done the next instructions, they're sitting there waiting to wait. This is a get instruction which says get the remainder register into a normal register. Afterwards, there's going to be a test for less than, then an increment instruction and a probable branch instruction. But those are still sitting in the fetch buffer because the LSS instruction has to go into an ALU. So ALUs were both busy. Okay, something happened there. We'll see something in the right buffer momentarily, I hope. Yep, there it is. 7. We just found 7 is prime. Okay. Okay. Let's go ahead. Let's go ahead here and take a look at the right buffer. It's going into the next byte now. Sorry. I wanted to see it when the right buffer is still active. So we'll go back. Right buffer. Come on, right buffer. Let's go. So at this point, we've just found that something is prime. Okay, you see, it's a little hard to recognize these primes maybe in hexadecimal. There's B, it's 11. D, you guys know your hexadecimal, 13. I've been practicing hexadecimal when I'm swimming. Instead of counting my strokes, I go 8, 9, A, B, C, D, E, F. It helps. Okay. So, all right. Now.
When you get past one digit, it gets a little
No. See, actually, the hard thing is after you get to, after 70F, then the next thing, no, I'm sorry, after 90F, the next thing would sound like 80. Because A and 8, would both say, so I say A as an OI. So I go 9 OI, B, C, D, E, F, 10, 11, 12, OI teen, B teen, C teen, D teen. I'm serious about it. It's important. Okay, so
Do you remember times table in hexadecimal?
no, not yet. I've only been swimming for I've only been swimming for a little while. So now this thing is still going again. But let's look at the at the version that has primes x. This is you see now the divide has this 10-cycle pipeline like this. Okay, so let's take a look and see how that looks like when we're getting okay, now here we actually have 2 division instructions in here. So the A, and because we also have another extra ALU, so one's waiting for the remainder of the first division, and so I start going, and it's waiting for the result of that one. Okay, so that allows some things to complete. A fetch buffer gets to move stuff out, and what happened to the other divide? That was supposed to take 10 cycles. What happened? Wait a minute. Is this a bug? What are we doing here? Go backward.
Maybe it's doing better than you expect.
No. What? This is a computer. We invented a new divide algorithm here. No. What? Well, but divide by 0 doesn't even take 6 cycles. I think it goes right into the. It goes right. Oh wait, that's true. That was a divide by 0. Why was it dividing by 0?
0 is not prime.
Yeah, but I mean, is this the one where I've actually tripled up the loop? Okay, let me see. This is primes x. Okay, primes x. No, I don't think it was. Well, we'll have to see why it divided by 0, I guess. Okay. Something has to go wrong in every demo, but where was I?
When I divide by 0?
When I divide by 0, it depends on whether the divide by 0 interrupt is enabled. And so I didn't enable it, so it just sets a bit in the arithmetic exception register, and it returns it actually returns a remainder equal to the original number and a quotient of 0, which is kind of reasonable because the remainder, like if you have to, and the quotient is 0, but that has the right effect actually. But by coincidence, it says the thing is it's actually a win. But now see, there's two things in the divide unit here, right? This is at cycle 525. So let me stop it and look at cycle 525, the Emacs. Sorry, I got to get Emacs up here, don't I? Okay, so this is primes x dot out, cycle 525. This is a slow machine. I actually have many more than 2,000 cycles on here, so this is a 13 megabyte file. But it should come out. Any questions while we're waiting? Well, I wanted to say one important thing. Okay, cycle 525. So it says it is got in the reorder buffer has a division instruction dividing 9 by 3, dividing 9 by 3, and it says, and then the other division instruction is dividing 9 by 5.
Second divide got squashed because if the 9 divided by 3
because it, 0. That's right. Very good. So after it finds out the remainder is 0, then this is speculative execution. So the division, So second division wasn't really necessary, it could be could be deissued. And so how do you actually animate the deissuing? Let's watch it.
It looks very much like a commit, which is regrettable.
Oh, okay. So you don't want okay. So there's a way to actually things go out of the reorder buffer at the bottom if you find out that something in the middle of the reorder buffer was a branch instruction that went the unexpected way, then you empty the reorder buffer from the bottom up. And the reason is that you have to undo the data structures. In fact, the reorder buffer has to be tricky. There can be a lot of things referring to the same register in that reorder buffer. Let me show you. See if we can get this on the screen. This reorder buffer like here. Suppose that there might be many instructions in here which this instruction might say set register 0 to something or other. Another one says register 0 to something. Another one says register 0. So 4 instructions might be affecting register 0 in here. All the instructions in between, all the instructions from here on refer to this register 0, but all the instructions in here refer to this one. All instructions in here refer to that one, and so on. So that's why they have what they call rename registers. The rename register holds everything in here is pointing to the rename register for this result, and so on. So when you deissue instruction, you want to do it from the bottom, so that things will now start pointing to this rename register. Okay, and as I was writing the simulator, it taught me an important lesson that writing a simulator like this with lots of parameters and lots of possibilities in the configurations was in some way I'm much more confident about it than if I were writing a simulator for an actual machine that had only a certain number of LSUs and FPUs and things like this, because I had to think big. I had to think of a reorder buffer that was 1,000 lines long. And I had to think of cases like this, which would never occur in practice on a real machine. Maybe only a certain register might never be able to be used more than twice or something like that, and the hardware wouldn't have to implement the general scheme. But in order to know that my algorithms were correct, I had to make them work in the case where you had a huge number of possibilities, and this meant that that was much easier to visualize the general case. If I was thinking small all the time, I would be every weekend I would have found another bug. Oh, I forgot, this could have been bigger. And so there's a great advantage actually in implementing something more general than you actually will ever build, because that forces you to think and makes it actually intuitively clear what the hard cases are that you have to handle.
When you misspeculate, do you clear only the portion of the reorder buffer that needs? You immediately deal with the misspeculation.
What I do is I say I've got to deissue 5 things or whatever it is.
You don't wait for the incorrect instruction just to bubble to the top.
No. What I do,
But you wouldn't do it.
What I do is before I commit anything more, I go from the bottom. So the general cycle says, is there anything to deissue? Then deissue. Is there anything to commit? Then commit. But priority goes to deissuing because I think I want to get things going.
You have to undo the renames.
And I have to undo the renames in reverse order.
Right.
The information was there. And it was, instead of letting it, so it's a trade-off as to whether I want to let it bubble all the way up the top. But I wanted to start the fetch going at the right address as soon as I could and stuff. So that's the way I implemented it. Certainly, all the way through the simulator, there were trade-offs. There were decisions like that to design. This one was the one that I chose, but I'm not saying it's the right or only way. Yeah. Good question, yeah?
Does the MMIX machine keep track of the addresses of each of the instructions that is executed?
That travels along with that travels along. in the reorder buffer, I keep the arithmetic exceptions, the possible interrupts. You know, if an interrupt occurs, you still don't know if it's going to be real because it might not get to the hot seat. But things like the instruction location are carried along with. It can be implicit, of course, in hardware, but in software, it might as well show the whole thing. Okay, so C primes. What am I doing? XX, right? Now this last example is for the is where I again have this divide unit, but and the same specs as before, but I changed my program so that it sort of doubles up the loop again. Not quite as it's actually simpler. I divide by three numbers at a time. So suppose you're trying to check if, say, 29 is prime. It would divide by 3, 5, and 7. Then it would test to see is the quotient less than the divisor. Then it would divide by the next 3, and then it would say is the quotient less than the divisor. This means that there are fewer instructions in between for loop bookkeeping. And, you know, fewer times that I'm actually checking the quotient against the divisor in the loop. And so we can watch what happens at a typical point in this.
More unnecessary divides, don't you?
Yes, I can do more unnecessary divides, but you see the pipeline, with this pipeline, it actually doesn't cost because the unnecessary divides are sort of masked. So yeah, the interesting trade-offs are going on. Like for example, here I have 3 things now in the divide queue, and every 10 cycles they'll advance. But you know, if I had to divide by 10 things before finding out, this time I'll divide by before finding out something's prime, I'll divide by 12 now. I round up to the next higher multiple of 3. But if it's not prime, I cut off right away anyway, because the remainder will be found to be 0. The remainder will be found to be 0 while it's sitting here in the reorder buffer, and it'll squash the other divides. I guess it's not quite as fast. So now here I have only one division going on. Oh, that one disappeared, turned out to be unnecessary because of the result of another test. Pretty soon we'll fill up with another divide. See, we're issuing 3 instructions at a time. So now you see the periodic pattern. The pink here are the divide. How many things we have in the, how many divides are pending? Often 3. And the dark green are the things that are waiting to be loaded, trial divisors, and the light green are the trivial bookkeeping operations, and the branches, tests, and things like that. And every vertical line is when I found a prime, and there'll be another glitch when I found a non-prime, like here. That shows in the trace. Okay, so you can. Before we saw this, we had no real idea what was going to happen with the algorithm, and you might look and say, oh, the fetch buffer is full now. Maybe we should have a bigger fetch buffer, because if we had a bigger fetch buffer, it would start fetching more instructions after. But that wouldn't do a bit of good as far as getting these guys unjammed, because it's waiting on this divide up here, and it would. Okay, so now I just want to compare the 3 prime strip charts so that you can see. Any questions before I shut this one down? Okay. Primes X. So, no, I'm sorry. What is it? Is that the CP? Is that what?
Yes.
Okay, CP, okay. So this is, At the top was the case where I tripled up the loop and divide by 3 things at a time. Here's where I'm dividing by only 1 thing at a time, but I still have this superscalar effect where and several divides can be going at once. And the other one was this guy, which is the case where the divide unit was taking the whole 60 cycles and not pipeline. Of course, it's very difficult to pipeline a divide unit. I'm not saying that there is an easy way to pipeline a divide so that you could do 10, 10, 10, 10. But if you could, this is how much you would gain. And so you see the primes are popping along somewhat faster. Not 6 times faster, though. The best way to make it 6 times faster is to figure out how to do a divide in 10 cycles. So anyway, this is something that amazingly the demo didn't break so far, and so we got to give a big hand to Robert and Chris. And the other thing I wanted to announce is that during the next few weeks, I'm going to be making some critical decisions about things about the MMIX as it comes out, and I want to have people to bounce ideas off of and to challenge my opinions and so on. So I'm planning to have a gathering at my house on Saturday, at least one Saturday, and probably the 27th of this month. So if people, no, this is only for people who are really seriously going to volunteer and want to not just to be there as a observer, but actually as a somebody willing to put time into helping me get the MMIX before I make too many bad mistakes. But if you are interested, this will be probably arranged through the MMIX Masters homepage, which is pointed to on my MMIX page. And if the date changes, that'll be announced there too. Anyway, that's coming up in about 3 weeks. Any other questions? Yeah.
I have actually 2 questions.
Okay.
First of all, I remember that 25 years ago I played with special languages for simulation languages.
Uh-huh.
So why didn't you use one of those? I bet they didn't die in 25 years.
Yeah.
They probably become stronger and faster.
And
the second question,
okay.
It may be even, I understand you love to C and C++, maybe this is the answer, but the second question is, there are new technologies on the horizon. For instance, mesh set with very long instruction work. And as I understand, the main quest in design of new CPUs right now is to have as much as possible of real estate on the chip and to utilize it efficiently, to make it working all together, to get more speed, more out of it. So, how extensible is your model? For instance, will it be able to cover things like mesh set, new features in mesh set, this kind of thing?
So I addressed some of that in the previous lecture, where my main goal is to have a good model that someone can learn and enjoy programming in, and not to get the maximum speed for all applications. So I want a general purpose computer that reflects the RISC methodology, but not to be the best for Fourier transforms or some kind of thing where a special application, physicists number crunching calculations. So I'm not trying to have the fastest computer for particular applications that are of high economic interest. I'm most interested in having a nice, clean, understandable, realistic model of a computer before they get ugly. And now, as far as simulation languages go, I actually also had a simulation language called SOL, a simulation-oriented language, which I withdrew when I learned about Simula 1, because I felt Simula was a big advance on it, which Simula 67 actually was after Simula 1, but Simula 1 was sufficiently better than my SOL that I said, why should I work on SOL anymore? and that was in Simula 1, and 67 was the beginning of object-oriented programming. However, with my knowledge of simulation, I still would have done this particular simulator the way I did. I'll publish it, and if somebody can do what I did in this program without, using some other tools, then that's great. But I didn't see how I was going to actually apply that object technology to actually do what I wanted to do, because I had to well, you could take this program is in C++ because it's in C, but it doesn't mean that I got anything that, I wasn't able to use the automatic features provided by some library. I still had to build my own building blocks, it seems.
But as I understand, one of the purposes of this work is to try to understand what problems arise in this kind of designs and to try to solve them maybe mathematically, just to come up with clean solutions for them. And new technologies are coming up with new problems,
Yes.
that will lead solution. In this sense, it would be nice if the model itself was extensible and be able to do tricks that hardware designers are inventing literally every day.
Yeah, well, I'm trying to do that by writing as a literate program, which means that people can understand what I did, but my attitude toward it is, rather than provide things that are black boxes that people plug into other things, I present something that has open, explain what's inside of it, and you massage it with your text editor rather than incorporating it as a module. That's happens to be the way I approach mathematics the same way. Some people think mathematicians are supposed to produce theorems, and the only thing is to know the enunciation of the theorem and the conclusion of the theorem. But to me, the important thing is the proof of the theorem, because in practice you have something that doesn't really fit the hypothesis. It's close, and it doesn't give you quite the result you want, but it's close. But if you know the proof of the theorem, you can adapt it to your situation, and that's what I try to do with my programs too.
No, I was always considering mathematics as very organized way of thinking.
Yeah.
Not necessarily not
Okay. Okay. So we're running late, but.
Professor Knuth, could you say something about how the pipeline advances every cycle? Can you say something about how you organize it? Did you visit the entire pipeline in reverse order?
So the pipeline. So the functional units each are either active or asleep, but usually active. They're waiting for something. And think of the cars in this shop. If there's first of all, if the car has to drive next into the thing on the next block, then the guy on the next block has to get his car out of there. So you might be stalled because something in the next stage is already blocking. There's another group of people still work on it. But if there's not a stall for that reason, you might be stalled because you're waiting for one of your operands. You can't add two numbers until the previous one has been computed. But if you got your operands, then you combine them and it goes to the next step. The typical, you can take a look at my program, but the typical thing says, is such and such happen, is such and such ready, do it. Otherwise, wait and reschedule yourself for the next time. And so you have to wait for locks these locks here. Are when there's competition for resources, and you can also have a situation where one of the instructions in the reorder buffer is waiting has locked the decache or something like that, but it turns out that instruction was issued on speculation. It's not really necessary, and so we have to unlock the decache when we cancel that thing. But the basic cycle is. At every unit of time, there's a bunch of coroutines in the program. Each coroutine is in a certain state. Like the load store, if you looked at my Emacs thing, it would say, it would show you that exactly. Here you see the reorder buffer. there's wraparound because we made a large font, but the divide, it says at the end state equals 2, okay? And it says divide 1:4. That means it's in the fourth stage of the divide pipeline. It will, and the next one is the get, which says Z equals greater than register R. It means it's waiting for the remainder register. It has to go into operand Z and the remainder register isn't ready yet because the remainder register is going to be computed by the divide instruction. Now at the next cycle, it runs the write coroutine, which is in state 0, which means sort of initial state. It finds nothing to do, so it schedules itself for time 527 in state 0. Then ALU1 is doing this get instruction. It schedules itself for the next time because the Z still isn't ready. ALU2 schedules itself at the next time. These guys are just sitting there waiting for the next time. And so that wasn't a very interesting time. Let's go for committing or something. So at cycle 553, back to 553, this instruction was no longer in. It was in the hot seat, and no longer in a functional unit. So it's ready to commit itself, and then we start running the write instruction. Again, nothing, and then these are do these things, and then here we issue a new instruction. That's sort of the general cycle. Yeah.
To follow up on that, does time ever jump forward in increments greater than 1?
Well, it could, but not. It's unusual. But they can go to sleep. So if it says running something and then like this running running ALU1, it wasn't followed by scheduling. So that meant it actually either went to sleep or it finished. In this case, it finished. But if something is waiting for the D cache to be filled, it goes to sleep, and the D cache filler wakes it up. When it gives it so that's the technicality, but it doesn't have to come up every cycle. But somebody will know to wake it up. And this is typical of simulation language type of things. Yeah.
If D cache is fast enough, and you can write at 1 clock cycle this data into D cache, I guess data buffer is not necessary. Is it correct? I understand that, for example, R3000 has a write buffer, but it's basically the D cache was very slow at that time. So if D cache is
there's different. Yeah, there's different. So the D cache has input and output. I mean, you have to put something new into the D cache, and then there's time when you flush the D cache down to the S cache or something like that. When you're flushing the D cache down to the next level of the hierarchy, which is either memory or to S cache, then it goes into a special buffer, and usually only one thing is being flushed at a time. So it goes into that special buffer right away, and usually that's because you want to replace it with some new information. So when you write into the D cache, usually you take the information that was previously in there. If you're not just updating it, you have to flush something else, and that goes into this separate buffer. And the separate buffer usually has to be there because you don't know if somebody else might be using the S cache or the memory that wants to get it. So this is called the victim buffer, I think. But usually they don't have two buffers like that. There's a lot of really interesting, but I was going around in circles on a lot of this stuff. because I couldn't figure out a truly elegant way to handle all of the cases of caches, considering all the possibilities that I can have write allocate, write around, I could have write back, write through, and all of these things could be handling them. And for 5 or 6 days I was spinning and spinning. I couldn't think of, I kept writing new drafts of the program and tearing it up and thing. And finally I decided the only way to do it is to throw code at the problem and write 10 pages of code for each case, and that worked. But I would have liked to find a truly elegant mathematical solution to all parts of this. It didn't seem to be possible. There's much more. Each part of it is understandable by itself, but the whole package together adds unavoidable complexity, I think. Well, thank you very much for listening.